In the two-dimensional kinematics chapter, we studied uniform circular motion. Right now what we want to do is revisit this topic, but from the point of view of force. So let's start the discussion by thinking about a hypothetical situation with a bowling ball that you throw, say, in a skating rink, so there's no friction, and we want to make this ball move in a circular motion, or something that is close to a circular motion. One way you could do this is to let the bowling ball move for a short amount of time, and then at the new location apply force F, let's say with a mallet, in this direction, so that you would give the bowling ball a momentary acceleration A that could change the direction of the velocity vector v1. After this force is applied for some short amount of time delta t, then the vector velocity will have changed from v1 to v2. The ball now moves along the new trajectory for a certain amount of time, and at the new location you apply the force again F with a mallet that produces an acceleration A for a short amount of time, which again can change the velocity vector from the previous vector v2 to a new velocity vector v3. You let the ball move along the new trajectory, and at the new location you hit it with the mallet again and again and again until you have brought the bowling ball back to its original location and velocity. To continue moving in this way, the bowling ball will have to be supplied with continuous forces applied by the mallet at different locations. All of these forces need to be applied pointing towards the center of the trajectory. This is consistent with the fact that we know that for an object moving in circular motion, the acceleration is centripetal, that the acceleration points towards the center of the trajectory. We know from Newton's second law that the net force acting on an object is equal to the mass times the acceleration of the object. So if the acceleration is to be centripetal to keep this object moving in a circle, the force also has to be centripetal. Only a force that has this property will be able to make an object move with constant velocity along a circular path. Since in uniform circular motion, the net force must point to the center of the circle, and its magnitude must be equal to the mass times the centripetal acceleration, we have that the net force acting on an object, any object that moves in a circular trajectory with constant velocity, the net force acting on that object must satisfy that it is equal to m v squared divided by r. You can also write this equation in terms of the angular velocity by replacing v with omega r, which gives you m omega squared times r. This equation is not telling you that there is a new force acting on the object that is equal to m v squared over r. It is telling you that whatever the forces that are applied to the object are, when you add those forces, the net force that you obtain, if the object is to move in a circular motion, must satisfy that it is equal to m v squared divided by r. Now let's think about the case when you're driving in your car and you take a turn. So at some point you're moving with some velocity, let's say in the upward direction, and as you take a turn, as the car starts to turn, well, the tendency of your body is, according to Newton's first law, to continue moving in a straight line with constant velocity. But the car, of course, because its interaction with the ground, the car starts to turn. As the car turns and your motion continues to be in a straight line, you will run into the window, into the door of the car. Basically, as the car turns and you continue to move in a straight line with constant velocity, what happens is that the door will get in your way. The door of the car will intersect your path as the door is moving to the left and you are moving in a straight line. Once you make contact with the door, then the door is able to apply a force on you that will keep you moving in a circular motion just as the car is. So from the point of contact between you and the door, the door will have to apply a force on you to keep you moving in a circle. Now, From the point of view of a passenger, from your point of view, or from the point of view of a passenger watching this happen inside the car, there seems to be a force between the moment when the car starts turning and when you make contact with the door. There seems to be a force that is pushing you towards the door. This force is usually referred to as centrifugal force, and it is actually a fictitious force because this force actually does not exist, even though it seems quite real for you and the passengers in the car. So why do we say that this force does not exist? That's because the car is a non-inertial reference frame, and in non-inertial reference frame, funny things can happen. For example, in non-inertial reference frames, we see objects accelerate even when no forces are present. And this is what's happening in the case of the turning car and the passenger. From the point of view of a person on the ground, there is no force between you and the car from the moment the car starts turning until you make contact with the door. From the point of view of a person in the car, which is a non-inertial system of reference, there seems to be a force pulling you towards the door. Newton's second law, however, tells us that in order to be a force, there must be interaction between two objects. Remember the situation with the ball inside the bus, and from the point of view of the passenger in the bus, and from the point of view of the chicken, which we discussed in previous video. From the point of view of the chicken, there is no force on the ball, therefore the ball just remains in place while the bus accelerates forward. From the point of view, so for this chicken, Newton's second law applies. No force, no acceleration. From the point of view of the passenger in the bus, the ball seems to be rolling down the aisle towards him or her, even though there is no force that is responsible for this motion. So for this passenger, F equals ma does not seem to hold. The passenger measures an acceleration, but cannot find any source for this force. So a system of reference that moves in a circle is also a non-inertial system of reference. And in these kind of reference systems, acceleration can be observed even when there are no forces present. Let me show you an example of this. The situation that I'm going to show you a simulation for illustrates what would happen from two different points of view when, say, a remote control helicopter flies by you if you are sitting on a merry-go-round going in a circular trajectory. From the point of view of an observer on the ground, which is an inertial system of reference, the helicopter is moving with constant velocity, which means that the net force acting on the helicopter is zero. The thrust from the motor is equal to air drag, and the helicopter moves with constant velocity. But let's see the motion of the helicopter from those two different points of view. Suppose that there is a red line painted on the floor of the merry-go-round. So from an observer standing on the merry-go-round, this red line does not move. The helicopter, represented here by the black dot, is clearly going to move. So the left-hand side of the screen is going to show you what this observer is going to see as the motion of the helicopter. On the right-hand side, we have the motion of the helicopter and the merry-go-round as seen by the observer standing on the ground. Notice how strange the motion of the helicopter is in the system of reference that is not inertial. Only very strange and mysterious forces could account for the weird motion in which the helicopter moves in this system of reference. In contrast, the motion of the helicopter in the inertial system of reference is quite simple. It just moves with constant velocity, given the fact that the net force acting in the helicopter is zero. The observer in the merry-go-round system of reference will not be able to understand the motion of the helicopter by simply looking at the thrust force of the engines and air drag, since Newton's laws are not valid in a non-inertial system of reference.